I'm starting the live stream. Hello and welcome back to another Chill Maths thing on Twitch. I'm James, and I'm going to do some more messing around with maths. I hope that's all right. It's Sunday afternoon in the UK. A little bit cloudy, a little bit rainy. And hello to Maths222222, who's in chat just before we've gone live. So good to see you again, because I think we missed you last week when we did this. And I'd like to talk about that a bit more. So we'll do a catch up, but hope you've been well. This is a bit of the plan. I think we're going to do some more whatever this is, and then possibly back to Hatcher's topology of numbers for our ongoing long-term quest to understand what's going on with continued fractions. Underappreciated art, I think, continued fractions. Can I say that underappreciated when I know very little about them? Is that me trying to sound like I know what's going on there? Ooh, yeah, it's very subtle, lots to learn about. Lots for me to learn about. Anyway, this is also me just trying to remember to set up the live stream. I haven't done this bit. There we go. I need one of these, don't I? And then I can actually draw. Where would I be if I couldn't draw all of the dots? Okay. Good. Hi, Mary. Hope you're well. Good to see you. Hi, everyone. Quick recap for what this is. So last week, things went a bit dotty. The idea is, and I'm going to say this several times, so don't stress, but the idea is that in the complex numbers, you can think about integers in the sense of things where the real part and the imaginary part are both whole numbers. You get this nice grid across and up. Those are called Gaussian integers. And they have primes and they have unique factorization, just like the natural numbers do. So we could try factorizing all of the numbers and visualizing their factorizations. And there should be loads of patterns going on in there. So a prime number in the Gaussian integers is one where the only factors are 1, -1, I, and minus I. There's kind of these four trivial factors that all complex numbers have factors of 1, -1, I, and minus I, and themselves, minus themselves, minus I times themselves, and I times themselves. So complex numbers come with lots of factors, 8 of which I consider to be trivial factors. We can show they're non-trivial prime factors. The way I've seen this visualized elsewhere is to have a kind of breakdown, splitting it into color-coded blobs for primes. So last week we put quite a lot of effort into putting loads of dots on the screen, and you get lots of grids. The grids are really hard to see, but there's quite a lot of square grids going on. So for example, this 1 plus 2i over here, how am I gonna do this? 1 plus 2i over here, that one is a Gaussian prime. One way to tell is that it's norm, which is the square of each part added together. So you're doing Pythagoras or something, so it's a squared plus b squared. A is crossed and b is up. A squared plus b squared. You get that norm. Its norm is prime, so the thing here, it's the complex number itself is a Gaussian prime. I don't think that's totally obvious, but there's some factorization going on behind the scenes involving that. And modulus is nice with complex numbers. Hello everyone. Right, good. Hi chat. I've missed Herb come in. Hi Herb, good to see you. And Mean Machine Rex is here as well. Hello Mean Machine Rex. Herb is a bit under the weather and has exams. Sorry to hear that, Herb. I'm a bit under the weather but no exams, so you outrank me on the sympathy scale. Yes, and what's this? Maths222 says, could you just use I as the unit prime and use the minimum number of them to multiply to make the number? Yeah, I suppose you could. People don't normally do that. People normally just exclude the units from their factorizations because you can always put some units in there. I think I know what you mean. So if it's over here, maybe it doesn't need any i's. If it's over there, maybe it needs an extra factor of I. You've then got to decide which things are actually the primes and which things are imposter I multiplied by the prime. So you need to break symmetry in the Argand diagram some way to say that this is kind of the true prime, and when I see this, I can use that as real 2 multiplied by this prime, rather than our hideous 2i times the thing over here. And because of that nice symmetry, my approach is to consider all 4 of these, or 8 of them, or whatever. No, I mean 4. All 4 of them multiplied by the 4 units to be just the same as each other. So I've tried to do them in the same colour. 1 plus I, but then over here would be minus 2 plus I, and down here would be minus 1 minus 2I, and then over here would be 2 minus I. Yeah, I think I got all those all right. I think I got those all correct. Brilliant, well done me. So around there, all 4 of them I would do in the same colour, because they're the same multi-units. And I'm not trying to visualise the eyes. Rice Cooker Man's here. Hello, Rice Cooker Man. We're doing this factorising Gaussian integers thing. Building a picture to visualise all the factorisations. And hello, Booman Will in chat. First time in chat, good to see you. Welcome along. Good to see you. This is what we've been doing recently on the stream. We've been trying to factorise complex numbers, bringing together perhaps anybody's love of prime numbers and factorisation with anybody's love of complex numbers and the Argand diagram, 2 dimensions on this picture, for a good reason. And let's do some shout outs to Twitch follows. Who's followed me? Oh, a bunch of people have followed me. Pineapple Man's Phone, Hyperextended Knees, Zero Duct Tape Chicken, Keat5, and Polar Ice. Good to see you all following on Twitch. I think I know what happened. Maybe we'll tell the story at some point for people on Twitch. I accidentally told people about my Twitch, which is of course much better promotion than telling someone about your Twitch. If you tell someone about your Twitch, they go. If you accidentally tell someone about your Twitch, they're like, no, I'm interested. Me Machine Rex, did I guess that you were Jammy Dodger the other day? Were you previously a custard cream? Is that what's going on? You were custard cream at one point and now you're Jammy Dodger, and I should look out for any biscuit related users in the future. This is my shrug for biscuit related futures. Right, okay, I think I've spotted the pattern. I only need 2 data points to extrapolate. Good biscuit choice. Right. We had Eve on the stream, so this is for work reasons. For the professional stream, we had Eve. Eve's great. She set some quite hard maths problems, and Chat did really well. I was really proud of Chat. I didn't want to gas them too much in front of Eve, but maybe next week I need to tell Chat that they did a good job. Sometimes I get like an external guest on, and I think, oh, Chat, come on, Chat, you can do it, and Chat really delivered this time. So that was good. So that's the professional work stream that I do. In case you couldn't tell, this is the unprofessional one, which is all about messing around. Anyway, big reveal coming in a second. So we did the dots last time to try and build this structure. So you have, for example, a prime, and then you get multiples of the prime. This is the real multiples of that prime. But then we'll also consider things like 2 plus I times that prime or something, right? Which means 2 times it plus I times it. And I rotates it around. So 2 plus I multiplied by that prime gives me this point. So you get these kind of grids of where the blue dots are in the picture. And I can't really do this, I think, especially with this version, which is a mess. But if you relax your eyes, then maybe you can see the blue dots in the picture. I don't know. See that they're in this kind of grid. 2 plus I and its multiples. Big reveal, which if you're in the Discord, you've already seen. But we'll do it on stream anyway. Oh, do I want to upgrade? Let's go not right now. So we thought about doing these as pie charts because there's an enrich activity where you show with pie charts what the factors are. For example, splitting things up. So here, this is 3, and then this is 3 times 3, and that'll be 3 times 3 times 1 plus I. 1 plus I is prime in this world. So you get pie charts like this. And I think what we could do is we talked about putting this together with a computer program to try and actually draw all of these and draw all the pie charts, and then uncharacteristically I went and did that. So reveal, here's the version that I made in between streams. I'm really pleased with this. I think it's actually good. So what you're looking at is Gaussian integers. The real axis is down here. So this is the origin, 0 is down here. Not shown. 0 is a little bit different for this ring. And then also not shown 1 because we're not factorising units, and I. So the real axis goes along this way. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. And you'll notice that some of those things have got factorizations in ways that they just don't for the integers, the real integers. I've used a grayscale thing for the ones that are real and prime. So for example, 3 here is prime. Strangely, perhaps, 5 is not prime. 5 factorizes in the Gaussian integers. And then we've got 7 and we've got 11. You might notice that these are the ones that are 3 more than a multiple of 4. They're equally spaced. It's a nice little Easter egg down the bottom there that those are equally spaced for a reason. Of course, the primes don't continue in that arithmetic sequence forever. But hey, that's what's going on with which ones are primes. And up this side, we've got a copy of that picture going upwards because this axis, the imaginary axis, has just been rotated by 90 degrees, it's been multiplied by I, so we get things like 2I. I'm not showing units, so I'm just showing the factorizations of numbers there. Let's talk about some of the kind of surprise factorizations then. In this world, the prime 2 has factorized, it has split. Both halves of this pie chart are the same colour because it's split into the same prime squared. That's maybe surprising. You can find that prime, it's here. This thing here is 1 plus I. And what we're looking at is the fact that 1 plus I squared, 1 minus 1 is 2I, and then up to units, I can multiply that by 1 minus 1I minus I, without affecting the diagram, the pie chart. So I get this 2I over here, right? But then I'm not showing you multiples of I or something, so I also put that pie chart here. So the number 2 has fallen. It's been factorised as 1 plus I squared. I mean, you can also see a kind of more interesting factorisation, perhaps it's 5. 5 has factorised because 5 is 4 plus 1, which is 2 squared plus 1 squared, which is 2 plus 1I times 2 minus 1I by the difference of 2 squares. It doesn't look like the difference of 2 squares, but it kind of is the difference of 2 squares. So it's the product of two primes, and they're the red and blue ones over here. There's some rotation by eyes or something going on as well, but these red and blue ones, they turn up in lots of places in the picture because they define quite small grids. They have small norm, so there's lots of red in the picture, there's lots of this shade of blue in the picture. Going further out to the rest of the picture, I love this so much. Going further out to the rest of the picture, you'll notice that there are some pie charts that are just one colour. Those are the Gaussian primes. And if you relax your eyes and look at the ones that are solid colour, you can see this lovely gradient going on from the kind of lemon yellow over here, all the way through oranges and pinks and purples like the sunset, through to blue to green to a very bright lime colour down here as you go around the primes clockwise. And we're using different hues for different angles. So I would say that Gaussian primes on the same angle would have the same colour, but in fact that never happens. No two Gaussian primes ever have the same argument, the same angle above the x-axis. Otherwise, it turns out that one would be a multiple of the other, which is the least prime thing that anyone can do, is to be a multiple of something else. Ugh. So in fact, they've all got different hues. I'm also playing with the saturation, which is a little bit unnecessary, but it gives the picture this nice air that things down this corner are quite bright colours, In particular, we've got these 4 primes: orange, magenta, pink, blue, and green down here, and the red and blue ones that are nice strong colours. And I like the way that they reappear quite a bit in the picture. And you can kind of track this dark blue colour turning up, for example, up here or something. 3 plus 2i, which goes here, and then here, and then here. And where else can I find it? Here and then here. There's kind of these like knights moves going on as well that you can now that I've got the whole picture, I can kind of show you that a little bit more. Let's try and draw that. So custom colour, that shade of blue. So starting at 0, 3 plus 2i is over here, and then you see a multiple over here, and then over here. But also, I should think about multiplying by I, which is instead of 3 across and 2 up, 3 up and 2 left to get over here. And there's this square grid going on where I can join them all up to show you where all of these dark blue multiples of 3 plus 2i are in this picture. So this one is going to be slightly off the bottom of the page. Yeah, there's one just off the bottom there that we can't see. But that's where the dark blue is in the picture, and I think it's just enough of it that you get a sense of where stuff is in this kind of grid. I've gone out to 11, partly to show you this prime at 11, and partly because we get a non-trivial cube just over here. I mean, what's non-trivial, right? Maybe it's a bit trivial. We've got a cube over here, which is just 1 plus I cubed, but I didn't feel that was very impressive. I put 1 plus I, colour-coded it to black, the same colour as the background, because otherwise you just get loads of it. This took a little while, but not a huge amount of time. I don't normally have much time outside of the stream to actually get stuff done, so it's good to actually spend some time drawing some pictures. Once I'd worked out how to factorise numbers, I might say a little bit about my algorithm for factorising numbers because it's alarmingly stupid. And we like that sort of thing around here. So I've pointed at this cube down here. I want you to notice that there's also a cube up here. That's not a coincidence. There's a lovely symmetry. I'm trying to show you this really weird reflection to reflect. If I get a right angle, there we go. I can do this. And then I just need to do a 45-degree reflection like this. Hey, that kind of worked. Sort of. I'm trying to do a right angle with my fingers. Reflection. Hey! So stuff comes back. So stuff on that side is like a mirror image of the things down here. Same shape of pie chart. Different primes, except for 1 plus I. 1 plus I is on that line, it reflects to itself. Everything else, the primes swap when you go over. So this one has a prime factorisation involving, oh gosh, which one's that? I think it might be this prime here. And then the one opposite up there has prime factorisation involving the opposite prime. Actually, I think it might be this pair in the middle. Oops. So 5 plus 6i has given us, yeah, this one over here. Yeah, so if you add those, you get 11, and the difference is 1. So sure, I think 5 plus 6i. Ideally, I'd be able to just look at the colours. I've discovered by making this that I'm really bad at recognising colours. I think you can get that. There's an app game where you have to spot which colour is like the odd one out, or which ones match. I'm rubbish at that, and now that's affecting my maths, so bad times. Anyway, I like this quite a lot. I think this is possibly one of the greatest things that we've put together on this Chill Math stream. Is that overstating it? No. What's the contention? What's the alternative? What else have we made? To the whole biscuit balancing thing. I don't think it's that bad. I can do red green. I can tell that this one is factorised into two numbers, and that's got 2 over there. So this red green comes up quite a lot, doesn't it? I think it's that one. I find it hard with these kind of pink purple shades, where or maybe we can play this as a sort of quiz game or something. I don't know. If I point at a number, ideally from this picture you could read off its factorisation by looking at the primes that are the same colours. And there's some tricky ones down this side. So this blue and green one, I don't really think I can pick out immediately which shade of green this is on the right. Is that it's one of the ones in that second row up? Is it the left one or the right one? I think it might be the right one, this one. And I can check that. I can do the maths because that's 6 plus 1i multiplied by 2 plus I. I don't know, possibly in a minus sign? No, I've got the wrong shade of blue as well. So this is tough, right? I've got to look at this green and blue. Work out where this is. Right. A t-shirt with chill maths above it. Ooh, that's an idea because the chill maths is like chill maths. Branding. Yeah, there we go. That's the shirt. I did use red and green. I can do red and green. Come on, chat. The chat's trying to gaslight me now into being colourblind, which, fair enough. I don't do the 5-dimensional one. Yeah, there's two sorts of... So they all have different hues because they have different angles. Awkwardly, the ones on this line have increasingly similar hues. So there's infinitely many Gaussian primes on this line, and the angles get closer and closer to 0 as you move along, which means that the hues get closer and closer to whatever kind of lime green 0 is. And similarly, along this way, they start off red, orange, yellow, red, orange, yellowy, orange, lemon, yellow, and then if you keep going, there's just lots and lots of more shades of slightly more lemon yellow that is pretty tough. There's a theorem that if you pick a range of angles, say some sort of cone, let's try and draw this. Oh, Myro, come on, you be cool. Be cool. Oh, no, that's not cool. We talked about this, Myro. Myro's not great at letting me just draw straight lines. Right, we're going to freehand it. There's a theorem that if you pick your favourite colour, which is maybe like that shade of lilacly blue, plus or minus a little bit. So you pick your exact favourite colour, or who knows, that might not go through any of these points. But if you have some sort of range around there, so some sort of narrow cone, I guess that's a narrow triangle or something. I'm going to call it a cone. Narrow cone, there are infinitely many primes, Gaussian primes in there. Sorry for the handwriting, that's got much worse than normal. That's Dirichlet's theorem, I think. I'm going to quickly Google that. Theorem for Gaussian primes? Is that what it's called? I don't know anything about it. No, I'm completely wrong. Good. Yeah, completely wrong. Okay, never mind. Somebody might look up a citation for that if I'm lucky. Primes of given argument or something? Any region? There's primes in every direction. What I'm rehearsing here is facts to tell people when they see me wearing this cool t-shirt and say, whoa, what's going on with your t-shirt? You've got to have some facts so that you can wow them with your primes knowledge. You could, I guess, tell them about the kind of aperiodic... Best use of the wow emote. Very good. Right, okay, let me try out another t-shirt fact. You might notice that these 1 plus I things, it's got a prime of course, they provide some of the most factored numbers because it's the smallest prime in some sense in the Gaussian integers. In the norm sense, it has norm 2. What am I writing? It has norm 2. So you get these things, these patterns where you get 2 of them over here. We wrote these numbers out a little bit last week and it was a bit of a mess. But you get this kind of structure where every other square or pie chart, every other pie chart has some wedge that's coloured black, and possibly multiple, with a pattern going like, so this row you only get 1 all the way through, and this row you only get 1 on a grid. But then there's a bit where you get 2. Can I do that? Where are the bits where you get 2? So you see sort of 2 regions of the pie chart because it's a factor of 1 plus I squared, and they form their own grid that is twice as large and offset a little bit. I need to think about that, I suppose. But they form this grid that is twice as large, where there are 2 bits that are coloured black. And then there are bits where there are 3, and they form a region. They form a grid that is twice as large again. Twice as large again? Oh no, that looks the same size. Oh, I've got to really think now, haven't I? Why is there a 2 here? Oh no, right, okay, back up. So I have to get the arrangement right because it's if you're wearing the t-shirt, you have to know. It's like being quizzed. If you're wearing a band's t-shirt, people are going to be like, name all of their albums. If you're wearing a maths t-shirt, oh no, name all the numbers. Okay, so where are the ones that have got 2? They're off by 45 degrees. Maybe that's not surprising because multiplying by 1 plus I involves a rotation by 45 degrees. But they have this thing that is, twice the side length. Root 2 the side length, maybe? Root 2 times the side length because I've multiplied it by something with magnitude root 2. Cool, so you get this larger grid that's at an angle, and then you get a larger grid that's at an angle again, which would be background the correct way round, like this. So that one is twice as large as the original ones. Then you look at 45 degrees and you get some that have 4 regions, and then you get larger and larger scales of these grids. Which means that it's got a kind of aperiodic structure. At one point I tried to understand the proof that the Penrose tiles are aperiodic, or that any of these aperiodic tiles are aperiodic. And I think I've got the main idea. I can't write out a proof, but I think I've got the main idea, which is if you have lots of scales to your picture, if it has lots of different scales, each of which repeats in a normal way, but if you have lots of different scales, then any translation will fail to translate properly some large scale. So if I translate this a little bit, then I might line up, if I translate 2 squares to the right, then I'll line up this kind of smallest grid. That'll be okay, but the huge grid won't be okay. There exists some scale where you've hardly moved it at all, and you definitely haven't moved it the periodic unit distance for that scale. So I think you can use this as a route to say there's a kind of aperiodic structure here, where the locations that have some black regions of the pie chart look quite periodic. There's lots of repeating going on, but the repeating is at lots of different scales, so it's not invariant under any translation. Of course, it's also missing a corner, so any translation is unlikely to be nice to that part of the t-shirt. Possibly you put, the 0 is really bad. Like it's invariant under translations for a more obvious reason, but possibly you fix that. I don't know. I feel like it's close to having something to say about a kind of Penrose tiling sort of thing, or kind of aperiodic thing. Maybe that's a reach. That one feels like a reach. People in chat. Megalomorph says something complicated about maths t-shirts. When I was undergrad, the math club made a t-shirt that said, "Attempting the impossible," on the back had a list of all the real numbers. There are only 30 numbers there. Good. Thank you, Math222. Gaussian primes in narrow sectors by Joshua Stuckey. Thank you very much. This is what I wanted. Yes. Perfect. It fires... Wait. If your argument is between phi and phi plus delta, what does that mean? What does that mean? Any theta greater than 7 over 2. X. Oh, right, okay, so some region where you have to... Oh, right, X is a number. This is a real interval first. Don't get ahead of myself. Good. Okay. Brilliant result. Thank you for the citation. Good. Nice. So you pick your favourite colour, and there are infinitely many primes over there. That paper had a bound on where to look if you want to find the next one. The results like this, I was a bit surprised to find you don't. What's the result? We don't know. You'd think that people would know whether or not there's a prime between n squared and n plus 1 squared. Because there are lots of prime numbers, relatively speaking. You know, not mostly primes, but there are quite a lot of prime numbers. So you'd think people would know if there's a prime in there, even for, you know, for all n. But I think that's open. I think people don't know that compared to the size of n squared, n plus 1 squared is actually quite close. Not close compared to things like the prime number theorem, which tells you how many primes you get. So in terms of heuristics, there really should be a prime in there. But I don't think people have proved it. There's the version, of course, semi-famous, of a prime between n and 2n, where the gap scales like the number. There's a terrible bound on how often you get a prime, but that one is known, semi-famously, as there's a prime in there. Hadoop has got a great proof of that uses central binomial coefficients. That, again, I'm aware of it, but yeah, we know about that one. Yeah, I have completely forgotten all of the names of all of the things. Who is that? Who's that for? Who's that? What's that called? Bertrand's postulate. There we go. Bertrand's postulate. Which Bertrand? This Bertrand. Not Bertrand Russell. Somebody with last name Bertrand. So you get a prime in there, which is not a kind of... It'd be misleading if you went through life thinking that there would be exactly one prime in there. That would be a misleading view about how many primes there are. People have proved that you get at least one. Proved by Chebyshev, says Wikipedia. Thank you, Wikipedia. I think that one's open. I went to a James Maynard talk, and I think James Maynard said that one's open. And if James Maynard thinks it's open, then it's probably open. Right. Okay. Good. So in particular, you can see what's the best thing in this picture. So I like the non-trivial cubes. Here they are, just hanging out, not being all non-trivial and cube-shaped. I like the kind of symmetric factorizations. So there's some that stand out a little bit, like this one and this one. There's this idea of complex conjugates going on, and prime conjugates. Possibly these should be the same colour on either side, but that ruins some of my fun. It's not really a cube. And I quite like the ones where you get nice bright colours that are opposites. So up here you get these ones that are close to the diagonal line. Do I have any feelings about that? See, these are semi-primes close to angle 45 degrees. Does that make me feel anything about, so what is this? 2 plus 3i and 1 plus 4i. How do I feel about this? Fine, I guess. So this is what's going on here? 1, 2, 3, 4. 8i and 3i, so 11i. And we've got real part minus 12. What am I doing? Sorry, I've just, you know when you completely forget what's going on? It's one of those relatable maths moments where I've just got absolutely no idea what's going on. Oh, how much can we reduce from the 2n? So I think reading that paper, the thing I was reminded of was that they had these intervals to say between x and x to the theta that took me a while to pass, with theta is 7 over 12, which is much worse than 2n in some sense, right? No, what am I talking about? What? No. Smaller. No, bigger. No, what? No. I've no idea what I'm talking about. I've no idea what I'm talking about. What was that paper saying? Can I get that paper back? What was that saying? A classical result of Huxley that I should go and read. Maybe I should go and read this paper, right? A classical result of Huxley states that if sufficiently large x and theta larger than 7 over 12, the institute... Oh, x plus x to the theta. Ah, right, good. Yes, there you go, Machine Rex. Apparently, there's a classical result of Huxley that says that instead of adding x, you only need to add x to the power of 7 over 12-ish. Then you get a prime. I'm supposed to point you to Huxley, Difference Between Consecutive Primes, 1972. Let's keep that one going in case we need that again. Yeah. I was, for some reason, multiplying together primes down here. We've gone just far enough that we've got these multiples of these interesting primes down here and the nice bright colours. Good. I think 11 is the correct number. If you go too much further, then things like this start to get a bit out of hand, because you just get more and more bits of pie chart. 7 seems like a nice thing. Good. Managed to answer a question I've got no right answering. How close together are... What's the smallest interval where we know that you will find a prime? For all n or something. Otherwise you'll just say between 2 and 4 there is a prime. Good, right, okay. I'm happy with this. Twitch, right. If you've joined us for interesting, colourful visualizations, I think I'm going to have to work out how to put this on a t-shirt. But now, I'm going to switch over to reading this textbook that I've been reading. One of the aims of this is to try and learn some new maths. We have done some visualizations, but I think it's textbook time. So I'm going to try and load that up. Right. Oh, that just crashed. Always a good sign. Always a good sign. Right, let's put that there. And then this here. Let's edit command what to let people know what we're doing. We are doing Hatch's topology. And it's 20 to 3. So looking good. Is that happy? Looks a little bit happy. So 1, 2, screen share, connect to app, paste the thing, Hatches, what are we doing? We're reading, get a verb in there, we're reading Hatch's topology of numbers, which is available here. Good. And then I accept over here. So if you want to play along, there's a link in chat to get the entire textbook as a free PDF, because Hatcher is cool. And I'm going to put this up on screen. Oh, that's too large. Twitch is really difficult sometimes for me. Is that good? Sort of okay-ish. So we'll bring it in a little bit. That's a bit better. It's quite a lot better. There we go. RFL, perfect. Okay, so we've been doing transformations on the fairy plane. Transformations on the fairy diagram to move around our continued fractions. Ooh, prime target. Sorry, I've been distracted. Me Machine Rex has been actually watching Prime Target on Apple TV. Did do the primes anyway. Is it true that in episode 1 he Googles what's a prime number? I think I saw that as a meme that Apple's new TV show about serious mathematicians doing breakthroughs in prime numbers starts with the main character, a graduate mathematician, Googling the phrase, what's a prime number? Let me know. Or possibly using Apple search to find out what a prime number is. Maybe that was a meme though. Maybe none of us have seen it. Have any of us got Apple TV? Is that a problem? Okay. It didn't work. It didn't cause me to get Apple TV. I think I'm the target audience for prime number thrillers. Yeah, I've definitely seen a meme that the main character Googles what's a prime in episode 1. Not a thing? Ah, right, okay. Just a meme. What I've done there, I should be aware of this. I have a tendency to take memes literally. Caused all sorts of trouble in the past. For me. Right. Okay. So if you just joined us for textbook fun, the textbook has lots of these diagrams, including the suspicious looking fraction 1 over 0, where the idea is that we can build any fraction using one simple trick, which is to take two fractions we've already got. Oh wait, a 0th simple trick is that we have two fractions like this, and then our simple trick is that we're allowed to add numerators and add denominators together. Wait, that sounds really stupid when I put it like that, because I will just, yeah, you can, what? Is that what we've been doing? That's what we've been doing. That's exactly what we've been doing, isn't it? More or less. Wait, hang on. So you can't add the... There's a subtlety to it to stop me from just adding A times the top one and B times the second one. What have we actually got? We've got, so you start with these two fractions. Where are they? Here's one and here's another. Right, so you can start by, you can have one of them. You have to choose which one you're adding, and you can add it as many times as you like. The other one is sitting still, being added to. But once you've done that, the thing that you're adding, not primes anymore, James. The thing that you're adding goes away. What are we doing? So you add along here, A1 times. Is this real? What are we doing? No, you add this lots of times. How does the median rule work? It's been a while since I looked at this. Like 2 weeks. I think maybe we were adding this one. 1 over 1, 1 over 2, 1 over 3, 1 over 4, 1 over 5 or whatever. And then, so the one at the vertex, you add that on top and bottom lots of times. So you can make fractions like this, fraction fun. I'm going to do 5 again, but who knows. 26. And then you add 5 over 26 onto this 1 over 5, adding above and below lots of times. So this has got this close relationship to the Euclidean algorithm, to doing repeated division, to highest common factors, calculations, things like that. Okay, and we've got these kind of fans. We're calling them fans. We've got the best fans. Of these triangles splitting outwards, and then the direction changes. Looks we're adding something different, and then the direction changes again. I'm adding that. You've got this kind of forwards and backwards ladder-like structure until we get down to our favourite fractions over here. There's a result. So here, so we're sort of, let's try and illustrate this a little bit. We're adding 1 over 5. Not really adding the fraction, but adding the numerator and denominator. I think that this would be, well, you'd understand this well if you'd seen vectors, because I think we often treat these like adding vectors. Yeah, it's that, isn't it? You can only combine together two fractions that you've got if AD minus BC is plus or minus 1. That's a good way of doing it. Maths 2. I like that. Right, so you start with two very basic fractions. You can add numerators and denominators, but only if the numerators and denominators satisfy AD minus BC equals plus or minus 1. Which is a bit mad, but that's what we're up to. So as you do the adding, it turns out that you can keep adding the same thing. It's just nuts, isn't it? What are we doing? You can keep adding. But then if you want to add something to that total, no, it's just silly. Okay, Mean Machine Rex has given me a hard stare because I may have spread some misinformation about the abilities of the main character of Prime Target. Yeah, adding only one. You're using the word type to help distinguish between which fractions we've got. You can't then switch to adding on the other one. But I can after. So it's weird. So if you've got 1-1, oh, tea time. Is it tea time already? Mean Machine Rex says tea time. I've still got a bit of tea. I'm going to go for tea in a second. Thanks for redeeming tea time. Trying to get in early. We sometimes need tea at 3 o'clock. Right, okay, hang on. I've got an idea. I've in trying to do a recap of what's going on in this textbook, I've realised I don't really understand what's going on in this textbook anymore. So I'm going to try and get there, and then I'm going to have a cup of tea. Tea time. That's the order of operations. So you can add these. We all agree. You can do the adding thing to get 1-1. But then something I was trying to say is that you can add 0-1 again to get to 1-2. Are you allowed to add 1-0 again? You must be allowed to add 1-0 again. How does it know which one you added? Oh, I guess that would be over somewhere over here. Right. Oh, so somewhere over here. There's another triangle up here where I add instead. I think of this triangle as me adding, going this way to add 1-0, and then add 1-0 again. Right. So there's triangles in lots of different directions. Okay, I can get on board with this, I think. Yeah. I hope you've taken over from Murray. Right. I didn't realise we had a sort of shift system. People earn channel points by being here, and you can spend channel points to remind everyone to drink a cup of tea, or alternatives are available, I suppose. But for me, it's going to be a cup of tea, and it's going to be very soon because that one is pretty cold. Right. We need like an on-screen on the stream or somewhere, maybe along the side. There could be like a live tea level, or maybe a temperature. If I had some sort of thermometer going that was also plugged into my computer, you could watch maybe the temperature going down. Like, we could really Tamagotchi this thing, is what I'm saying. There could be several indicators about how things are going, and you would have to press buttons to try and keep all the meters up. Right. Okay. So we've got transformations coming up on the stream. We've got transformations of this that turn it into a different fraction at the end, I think, or something. This will help us understand continued fractions. Maybe they're in here too. Base COPD. Then you get the plus minus one stuff about whether you're doing a translation, translation. So we can do transformations that move edges around, and we've got this way of tracking orientation based on whether something is +1 or -1. So we move this edge by a sequence of pivoting transformations, one for each fan. Oh goodness me. Well, first pivot is the edge pivot across a fan of A1 triangles to the second edge of the zigzag path. So the pivot is a bit like rotation around the point. Maths222 made this animation for us that I can try and find. Let's see if I can find the pivot animation. So yes, here it is. Thank you for making this Maths222. Here's the fairy diagram. It's, goodness me, it's a lot of fractions around the outside, and they're connected if they have this condition AD minus BC is 1, where the fractions are A over B and C over D, and you look at whether AD minus BC, so numerator and denominators, AD minus BC is plus or minus 1. You have to say plus or minus 1 because I don't know which way around they are. But if it's plus or minus 1, then you draw a line, and then there's this nice transformation you can do where the whole thing rotates a bit in a way to move what was an edge to an edge. And this is good because all of the triangles go to triangles, all of the points go to points, all of the edges go to edges. It's got a pivot. This one is pivoting around that top point, which represents the number 1 over 0 or infinity. And it sort of moves everything around so that if you had a wedge of triangles that you were interested in, well, you now have the next wedge along, or each triangle is moved along one space in that big pivoting thing from infinity. Those are triangles, even though the edges are curved. They've got 3 corners, they've got sides. That's good enough. I can trace the transformation. Yeah, but I have to think, right? I have to change these. A few weeks ago, I remember taking about 10 minutes to work out these. This is, yeah, good job. Thanks for building this. We've got very talented Twitch chat here. The best viewers. The function f. Wait, where's f? Oh, that's this. But I can't think of anything creative. Can I divide by 2? Is that fun? Wait. It's a disaster. Oh, I need to put a Z over there. Divide by 2? Is that fun? A different transformation? So halve everything? I don't know what's going to happen. Nothing. Nothing has happened. Absolutely nothing. Has no n in it. Yeah, of course not. So m plus 1 to sort of gradually get us from, yeah, thanks, gradually get us from z to z over 2. That's better. There we go. Now that's what I call a transformation of the plane. Transformation of something. It's not very successful, is it? It hasn't ended up where I wanted it to. Oh yeah, because integers are not... I've got to preserve everything. Right, hang on. I think I'm going to stick to adding n. Thanks for the invitation to edit this thing, but I think we're going to stick with that. I can move 2. If I'm brave, I could shift it along by 2 triangles. There it goes, it's doing it again. Whoa. There we go. Along twice. Watch those lines go. There's the first one. And then a second one, but I don't think I trust myself to animate any other transformations of this. Also, I've started making it a bit lopsided. These are supposed to go on forever. For Desmos, you can't tell Desmos to go on forever. So that's just me. So other transformations of the reals that preserve all the integers. I suppose maybe I'm supposed to pivot around something else. Yeah, I can't think of anything. Multiplying doesn't really work because you have to end up with the integers. Is it just translations? No. If you're preserving infinity, then maybe it is just... If you're preserving that corner and not doing a reflection or something, maybe it is just these translations. No, I didn't know that. So somehow I get more levels of detail in some of these thoughts. Anyway, good stuff. That was a good transformation. This is the point I wanted to illustrate. I'm going to do quite a lot of those to translate shuffling along to work out what sort of symmetry we've done overall, and it depends whether there's an extra flip or not. Do a lot of pivots, put it all together, which way you're going, to clockwise or anti-clockwise as you go along, alternating clockwise and anti-clockwise directions. These are the matrices. Crikey, okay. End steps. We've seen matrices like these before. Good. We've looked at quite a few things. Does it do multiplication as a transformation? I can't see it. Because you've got to end up with all the integers at integers, 1 to 1. I can't see how multiplication works. This is for a transformation of the upper half plane that perhaps keeps infinity at infinity. What else can you do? I don't know. There's some with some inversion. Ah, thank you, Mean Machine Rex. It's a great idea. There's the tech we need. Also, we'll make a really intelligent mug. If it's an Apple Watch, then we'll get its heart rate as well. So we can check on the vitals of the tea. Right. Okay. Here we go. There's a problem, and then it's going to two problems. They're going to cancel out, which sounds like fun. Two things wrong with this product. First, the order of terms appears to be backwards, right to left. So this product would pivot AK steps and AK minus 1 steps, whereas we want to move that edge forwards. The other problem is that each pivoting transformation of the product is pivoting about either 0, 1 or 1, 0, whereas the pivotings that move that edge are pivoting about a sequence of different vertices. Surprisingly enough, these two problems cancel each other out. It's actually correct and does equal the thing that we want to make this transformation, ABCD. To see why, and now there's going to be an argument, which I'm going to read, but then I think I'm going to need a cup of tea. To see why, suppose we superimpose a copy of the strip on top of the circular fairy diagram, but with the right edge lying on the top of the edge 1, 0, 0, 1. Oh my goodness, what? And each triangle lying exactly on top of the corresponding triangle in the lower half of the diagram. A corresponding triangle in the lower half diagram. What? If we apply the last matrix of the product to this repositioned strip, this pivots the strip so that the next to last edge of the zigzag path lies on top of 1, 0, 0, 1. Here is the kind of picture that I've got in my head for this. Where's 0, 1, 1, 0? I think that's north-south. So you have some sort of sequence of triangles in the circle. I can't draw circles, but in the circle you have some sequence of triangles all ready to go. I've got them in my head, they're alternating colours as a sort of zigzag path, like a sort of zebra stripe thing over here. And there's this 1 over 0, 0 over 1 line in the middle. And now we're going to imagine feeding them through to say, where do you end up? If you do some pivots around 1 over 0, then you pivot over here, and then you're also ready to do some pivots around 0 over 1. So as you pivot, where do you end up? You're sort of pushing it through into the positive half of the numbers, or whatever, pushing it through into the right-hand side, and then doing these pivots, which move the whole thing around as you go. That's really hard to imagine. The book would like me to imagine that. The next to last edge of the zigzag path lies on top of 1, 0, 0, 1, so the next to last edge. As we go through, we're going to push these edges through, either rotating up or rotating down. So doing this pivot around infinity that Desmos just showed us, or doing the kind of opposite one where you pivot around the bottom point. So maybe we should have that. Maybe we should have a pivot around 0. That's the multiplication. That's pivot around 0 would be some sort of multiplication, right? No, I'm also preserving infinity if I do that. Tricky. Can't see how to put n in it for a visualization, but you need to get from something like one of these 1 over z's. sort of things. It's going to flip everything inside out. I don't love it. So it's going to keep sort of feeding things through. I can kind of see you've got some little handles to turn maybe around here and around here. And it's pushing through this kind of mangle, pushing through the stripy sock through the mangle, and it's going to end up flopping around over here somewhere. And the idea is that if you do this in the right order, then you can end up with the point of the toe of the sock ending up at just the right place in this diagram. Let's have a quick look at the decimals again to see if that makes any sense. So we've got maybe this region followed by this one, this one, this one, but then some of these. And as you push through, you're pushing this first triangle through and ready to make a decision about how you're going to push through the next bit. But pivoting around this thing down here brings the whole thing down. So I'm a bit sort of surprised. You've got to plan ahead a bit because later decisions that you make are going to spin the whole thing. So notice how notice how bits of this part of the picture down here all gets moved up there. It's quite a large move. All of this stuff, look, it's shot up to the top somewhere and scaled down. I didn't really do that, but scaled down over here. So it all ends up over here. Each time I press this button, stuff gets moved quite a long distance. So you've got to plan ahead. So there's kind of a little bit of working backwards, but also planning ahead to work out where stuff's going to end up after you've turned this handle and that handle, which does kind of opposite thing, a certain number of times. Are you all imagining this? You've got sort of two handles to turn, you've got a stripy sock going through, and as you turn the handles, it's going everywhere. Mental image. What happens when the left side runs out of triangles? There's not really supposed to be a gap here at the top. It's supposed to keep going forever. We haven't really been able to convince Desmos to draw infinitely many circles, but it's doing quite well to do this sort of infinitely many. The animation at the moment sort of pops an extra one in each time you play it. Is it this slider for number? Yeah, there you go. So there's lots more up there. Maybe that's more convincing. My computer fan's just switched on. I'll click the button. If this crashes the stream, then it crashes the stream. It's crashed the animation. Oh, right, okay, that's the best I can do. There you go. 1 frame a second. Pop. Yeah, but there's sort of lots going on over there. Let's go for 10 again. Resolution is the depth. This is even worse because this one affects how many layers of circles it draws. Put that back to 15. Yeah, I was worried about this slider down here. How many triangles it's going to draw. I think that one can really get out of hand because it has to draw quite a lot of very small triangles. Number of polygons. It's not even drawing polygons. I'm not even sure it's drawing lines. I'm terrified that it's drawing like for each green line. I think it might be doing quite a lot of work. Is this a version of the one that I did? No. Maybe? Oh, it's a collaborative thing, maybe-ish. Oh, no, you've got some fun stuff going on. You've got some fun stuff. Yeah. What are you doing those polygons? I can't remember how you're drawing the lines. Possibly each line is made of lots of little line segments. Right, okay, they are polygons or something. Okay. I find Desmos really hard. We've got Maths 2 to 2. Good. Okay. Oh, that's why you've got your exponentials, right? Where are your exponentials? T1. Yep, okay. Is that pi? Anyway, so you've got these different, I see. So that's sort of discretizing your circle to have a vector around there so that it can do all the things around the point. Good. Right, okay, good time for a cup of tea for me, I think. I'm going to run an ad break. I'll be back in a couple of minutes. to I don't know, read a book or something. What are we doing? Reading this book, which hopefully is going to get to some sort of result involving continued fractions at some point in this chapter. I think we will find out. If you want to get ahead, you can read the link in the What chat. The link in the chat points you to the actual textbook that I've been reading for the last several months after someone said I should read it a couple of years ago. You were looking at, well, briefly, lots of circles that are orthogonal to the unit circle with a complex transformation, moving all of them around in a way that maps triangles to triangles. We'll play it one more time and then hit the ad break. Thanks for joining, chat. Good to see you. One more time. It's a transformation. All of the circles that, not all of the circles that are orthogonal, but lots of circles that are orthogonal to the unit circle, corresponding to lines in the fairy diagram, transforming by all moving along one triangle in a particular direction. Good. Right. Tea break. Thanks for hitting the T button, Mean Machine Rex. We're going to play Placemats and be back in a couple of minutes with a fresh cup of tea. See you in a second. I'm back. A bot managed to get in. I'm going to have a quick look at my bot settings. 2 seconds. But I don't know why I've unmuted. I've unmuted and switched on my camera just to be like, oh, I'll do some settings. But I always come back from the ad breaks like, how does Twitch work? Right, Cloudbot, what are you up to? No, I don't want any themed overlays. I would quite like Cloudbot. Is it Cloudbot that does my banned words? I think it is. Word protection is on. Where's my word protection? Blacklist. Purge. Did they use a capital letter? Was that the problem? Let's go. Let's just add. Okay, right. Let's see if that works. Okay. The punishment is purge, not ban, but whatever. Okay. Anything else happened during chat, during the break? People discuss what sort of tea they have. Mean Machine Rex wants me to look at a Desmos. The Desmos is pretty groovy. It's one of these. I know what shape this is. It's called a hypercube, isn't it? It's doing a rotation around some axis in 4-dimensional space. Good job. Very nice. That looks great. I like the way all of the cubes are sometimes there and sometimes not there. Sometimes they look like cubes, sometimes they don't look like cubes. Oh, I've just noticed it's also spinning around another axis. I have to allow for that. If I'm trying to work out which axis it's spinning around. I don't think it's rotating around a particularly nice axis. Nothing is staying still. Right. When are we doing the t-shirt? Right, yeah. I had to think about this over the kettle. I thought one way to do the t-shirt is that I just put the graphic. I should put the graphic on the website, and then people can download the graphic and print it on like is Spreadshirt still a thing? And then maybe the complicated way to do t-shirts is I actually work out how to make t-shirts or something. But I don't think I have copyright on the complex numbers. Imagine if you had copyright on the complex numbers. No one would use the complex numbers for anything. They would all be too busy being cross with you. Okay, yeah, I think I've used this website before. Okay, I will try and work out how to do t-shirts, partly because I want a t-shirt, and partly to let you get t-shirts or something. I think we can get through 2 t-shirts at least. That's the plan. It started as a t-shirt. This thing has gone from t-shirt owned by somebody else, t-shirt owned by somebody else, to internet content, switches to different internet content with us, switching back to t-shirt again will complete the loop, especially if the 2 t-shirts ever meet. Going all the way around. Yeah, spinning and also spinning and being projected. So this thing, yeah, if you take a cube and you spin it around a weird axis, then look at the edges. The 3D to 2D projection is about that complicated, so seems about right to me. Anyway, what am I talking about? Of course it's spinning. What on earth is that picture on the left? Some sort of like demonic sigil, isn't it? It's got these like horns and arrows and a sock going through a mangle. It's like, right. Yeah, I just need to sort of Shopify. Ching! I get a lot of adverts for Shopify and Squarespace. I should use Squarespace and Shopify. Set up my t-shirt empire. Oh, I could sell my PhD t-shirt as well. This is going to be a great t-shirt shop. Right. Good. Yeah, there's bats and arrows and horns and things. Terrible. Right. This paragraph is trying to convince me that if you send the sock through the mangle, it ends up at the correct edge, which I'm just going to believe, I think. I'm still waiting to see where this is going, I think. Oh no. There are other three possibilities. It turns out I haven't understood what's going on at all. Aren't these all the same? No? This seems fine. This is what we were just doing, isn't it? Pivoting around 1, 0 and 0, 1. As an example, consider this corresponds to the edge. So a matrix represents an edge because it links together two fractions, which are a bit like vectors, and the condition that AD minus BC is 1 or minus 1 is a bit like the determinants of that matrix. Okay, so we get these. First figure below. Similarly, for this, which is the same but backwards and upside down, we have this continued fraction, as in the second figure. So this is a different diagram, but it looks really similar and corresponds to very similar numbers at the end. They're reciprocals and they're the other way around. Which means that that's got the same determinant possibly, because it's two sorts of opposite. Other way around and other way up. Switch the rows, switch the columns and switch the rows. It's probably got the same determinant. Okay. Right, great, loving it. Perfect. We're doing some sort of translation of this stripy sock that's going off towards our favourite edge of the fairy diagram, which is relevant, I suppose, if we want to draw all of these things in Desmos diagram. Maybe we need to know where they are, how to generate them. That's been a tricky thing for us trying to make the visualizations, is trying to work out how to list all of them, how to list all of the edges. This condition that we keep coming back to with two fractions such that AD minus BC is 1 or minus 1. If you can list those efficiently, then you can draw the picture more efficiently. Art stream. Yeah. Sock going through a mangle is probably the highlight of the art. Okay. This produces adjacent pairs with 3. Oh my goodness. Each of these pairs found we can make it. I no longer have any idea what we're doing, but I'm going to sort of push through. I'm a tiny bit under the weather. Can I use that? Can I play that card? Cannot be expressed. Okay. Pivots are orientation preserving, but glide reflections and a single reflection, please. I know. Products of simple glide reflections. Each move an edge across a single fan, but orientation reversing. You use an odd number of those. Orientation reversing an odd number of times will get me back, I think. It's that transformation. This transformation takes the edge to over there and is orientation reversing. A transformation with a matrix like this has similar behaviour. Left edge to the preceding right edge. This glide symmetry, reflection and symmetry of the infinite strip obtained by the first applying the glide reflection of the infinite strip to get a strip twice as long. They're taking the periodic extension of this double strip in both directions. Oh my goodness. We've got to balance the biscuit on the wall. We did a whole like month of streaming about this, about balancing biscuits on walls. It was balancing perfectly. That was the art there. What is all of this doing? This is telling me how to. Okay, recap. We're trying to work out what's going on with continued fractions where the continued fraction numbers are periodic. Then we get a bit of it that repeats lots of times. And in the fairy diagram, there are these fans that spread out in opposite directions, and they correspond to the numbers in the continued fraction. Because of this kind of repeated division and these ideas about doing the same thing again but over here. Anyway, so if it's periodic, then we're understanding that in terms of an actual transformation that transforms these numbers are the same as those numbers down there, means something like the transformation that takes these ones over there is the one that takes these triangles in the fairy diagram over there. So that's why we're doing these transformations. We're interested in ones where you could repeatedly do the transformation to get down to the continued fraction of something, it's going to turn out that the fact about continued fractions that we're building towards is that, well, once you get there, you have a root of a quadratic equation, I think. Right. Oh, I hadn't considered doing really good art. I could do really good art. Okay. Right. More generally, what's going on then? What's going on? We've got these transformations. Got to be flipped over. For any matrix of positive integers with determinant plus minus 1, a thing we care about a bit, there is an associated strip from the edge. Strip of triangles from this to get there. So we sometimes think about the matrix representing this edge, and sometimes we think about the matrix taking this edge to that edge. We express those matrices as the basic matrices like this. Is that n in each of the corners surrounded by 1s? It is, isn't it? N, 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 n. Round it goes. Lovely stuff. By putting arrows on the edges of the zigzag path in the strip to indicate the orientation of the edges. Oh my goodness. So these are coming out of 1, 0, they go both ways, but then it follows that path. Intermediate edges oriented arbitrarily. Oh, because you want to get the start orientation to match the end orientation, but you don't really care if you flip it around a bit in between. It's like pancakes, you want to get it the right way up at the end, but in between anything goes. I'm not good at pancakes. Here's a product, and this is going on. Okay. Okay, great. Don't make me do the exercises, chat. We're not doing the exercises. First drawing. Oh my goodness, look at these exercises. First draw infinitely many triangles. Then find a transformation that explains what's going on with all your triangles. And then solve T of Z is Z. I kind of get what's going on. My suspicion is that the triangles are not doing a lot for this proof, but this one, for example, is going to be something like there's a triangle, and then another one the other way up, and then this one means 1 this way up, and then this one means 1 that way up, and then the 2 means 2 that way up. 1, 1, 1, 1, 2. 1, 1, 1, 1, 1, 2. I have not enough ones. So this kind of strip of triangles with this long line down the middle that joins up like this, but with an extra line here, and then that repeats. So there's kind of the repeating thing going on. So the transformation is going to be whatever it is that takes, how do I label this? 1, 0, 0, 1. And then count along here, find the transformation that does that, and that's T, and then go for it. I don't want to do that. That sounds rubbish. I'm going to do it anyway. So add these, add these, add these, add these together, and then add the top one twice to get 10 over 13, and then, surprise, 15 over 21. Not 15 over 21. 29? No, 8. How do you add? How does adding work? 3 plus 5 is 8. 8 plus 5 is 13. 13 over 21. So the transformation is something like, when it takes 1, 0, 0, 1, 2, 5, 8, 13, 21. So is it something like 5, 8, 13, 21? Or possibly I need to write that the other way round. Not sure. 105, 80, 24, 104. So determinant 1. That looks good. Orientation preserving. Find the fixed point. That's T. Find the fixed point. T of Z is Z. Should be good. Maybe that is nice. Maybe that is nice. I don't know. I didn't have to write down any fractions. What do I hate more, triangles or fractions? Questions that mathematicians must think about. Right, okay. Find an infinite periodic strip. Dude, yes, it goes. Transformation like this is a glide reflection, and it's a translation along the strip. So glide reflection would be flippy, but then doing it twice would flippy it back again. So what do I think? 0, 1, 1, 2. 0, 1, 1, 2. How do I make that? So that makes me think that it's something like 1, 0, 0, 1. But then to get to 1, 2, so I want to add this 0, 1 to get 1, 1. And then 1, 2, I want to add this. This doesn't look glide like to me. Oh no, I want this edge. I want this edge over here. Not that one, which is 1, 1, 1, 2. So how am I going to make that? How am I going to make that? Good question. 0, 1, 1. So 1, 0, 0, 1. Let's start 1, 0 up here. 0, 1 down here. And then I'm supposed to add, right? Oh, so I add the bottom one twice. Add the bottom one twice. So add the bottom one twice. And you get to 1, 1, and then 1, 2. So I added the wrong direction to get to this thing. So then there'll be a glide reflection to get us to this shape, and then, so we're looking for the thing that takes this line to that line, and that flips us upside down, and then keep going. So it's going to be this, I think, because then we get to 1, 3, 2, 5. So to get to this edge, we'll get this 1, 2, 2, 5. So I think it's this. Some of these are supposed to be vertical, and then there's these thick lines. But it goes like this, I think. 2 up, 2 down, 2 up, 2 down, 2 up, 2 down. Right, here's a continued fraction. Same periodic strip to completely continued fraction for that. Don't really feel like doing that. No, yep, can't remember how that works. And then finally, what's this? Final elements of LFZ, whose matrix has at least one entry equal to 0. Determine their type and determine how they act on the Fairy diagram. Oh, is this the final transformations thing? And Maths Tutor 2 wants me to do it because then we'll understand all the transformations. Let's have a quick shot at it. So if it's this, at least one entry equal to 0. So we're looking for A, B, C, D, such that AD minus BC is plus minus 1. Look for this with AD minus BC is plus or minus 1. And with at least one of them 0. So maybe we have 0, BD like this, with BC equals plus or minus 1, which is these, minus 1D. There's minus 1 stuff going on as well. And then we have basically that but rotated. And also we have things like where D is 0, and A can be anything, and you want 1s and minus 1s. Minus 1, 1, minus 1. Oh, so minus 1 on both would be a case as well, because that would give me minus 1, D. That's also fine. Yada yada yada, 4 of those, and I reckon you get 4 of the others as well, where you have a 0 surrounded by some things that multiply to give 1 or minus 1, and then I don't care what number this is. So 4 of those, and then 4 of these as well, with the different plus and minus signs. So like 1, minus 1b, 4 of these. Okay, and there's some overlap between my cases because in some of them you can have 2 zeros, like the identity matrix. Everything's fine. Work out how they all act on the Fairy diagram, don't know. Don't want to think about it. I really don't want to think about these as compositions of pivotal transformations, I'm sorry. It was like matrix factorization into the matrices that we had. So something like interpret that as a transformation for edges. Work out the triangles in between, and then read off the pivots along the way. So for every orientation preserving element of a left set. That's sort of what we did, isn't it? Products, pivots, representations. That's sort of what we were talking about with the sock going through the mangle. Okay. Fair enough. That is, I think, miraculously going to be the end of chapter 3. And I can't remember what's in 4. It's quadratic forms. This seems like quite a good switch. I think we might be back in business. Because this is which numbers can be written as the sum of two squares, which is strongly related to which numbers along the bottom of the t-shirt factorise and which ones are actually primes. If you understand the answer to that, then you'll understand why some of the primes along here have factorised and some of them have been rendered in grey circles. Okay. Oh, I think I may have hit a second wind. Transformations of the diagram, fine. Quadratic forms, maybe. I've been wondering for about 2 chapters now. Are we getting back to the kind of prime number stuff? There was some prime number stuff right at the front of the book that got me hooked. And then quite a lot of triangle facts. And moving the fairy diagram around, which I didn't enjoy as much as I thought I would. But now, maybe we get to do some prime facts again. Yeah, when does an equation x squared plus y squared equal n have integer solutions is something I've been wondering about, because that's how you find, well, that's how you know. I've been interested in whether that's prime or not, like if x squared plus y squared equals b. Because if you're looking for primes on the t-shirt, then you have like x and y for the coordinates, and you'd quite like to know, is x squared plus y squared prime? I mean, that's easy, right? You just check if it's prime or not. The converse, though, which primes can you get? Okay, plug in values for x and y, and you get these solutions. Some of these can be written in 2 ways, right? So 25, how have they done 25? Oh, there it is, 2 ways. Nice. In some cases, more than 1 way. Good. First goal would be to describe a more efficient way to find the integer solutions. Ooh, okay. And display them graphically. Yes, please. The solution for doing this will work not just for the function like this, but also the function like that. This is called a quadratic form, or possibly in this book, a form. When someone introduces you to a notation and then a short notation, you have to be aware that they might be planning to use the short notation. Goodness, probably not maths 2. Or at least not for a couple of chapters. And I'm getting through about a chapter a month at the moment, so woo! Right. Representing a wave form Q means you can find some solutions for that value of n. Which numbers n can you do? And how do you find them, maybe? Not very interesting. Okay, not 0, 0, fine. Before starting to describe a method, if the greatest common divisor of 2 integers is d, then we can bring out the factors of d, and so you have d squared as a factor of q. Hence, it suffices to find, it's enough to find the values of q on primitive pairs like these ones. So the pairs whose greatest common divisor is 1, and then multiply these values by arbitrary squares, d squared. Yeah, because if you want to make some sort of value, maybe you can make it with a primitive pair, hooray! Or maybe you can multiply up. So if is the converse true? If I want to make 36, do I have to be able to make 1? No. "36" was a weird choice. If I want to make 18, do I have to be able to make 2? No, I don't think I do. 5 months left, yeah. Something like that. We're on page 97 of 362. No, I want to go back to thinking about that. Sorry, I've got myself stuck in a converse. We define solutions on primitive pairs. Solutions on primitive pairs, and then multiply it by d squared for all values of d. So if I'm interested in making the number 18, then maybe you can just make 18. For example, if the quadratic form is x squared plus 18y squared, then maybe you can just make 18 by plugging in 0 and 1. You can just make 18. And the fact that 18 has a square factor is kind of irrelevant, because it's not like you can remove that square and say, well, first make the number 2 and then multiply up, because you can't make the number 2. But you can make the number 18, so you are fine. Okay, so the way around that this works is that this is constructive. If you can make these numbers, then you can also make d squared and times those numbers. And if you're trying to make a number, you can't necessarily, if you have a target, you can't remove factors from your target just from n. Oh, hey, Unstucky, how you doing? 3 time zones, and I'm now early in the morning or something. Sorry to hear that. We had a paper by a person called Stucky on screen a while ago, talking about Gaussian primes in different regions of space. It was good. Yeah, so it depends. Maths Tutor 2 had got something about Lagrange's four-square theorem, but it depends if I'm thinking about sums of squares in particular, or if I'm thinking about quadratic forms in general. And this fact, I've got to think about pulling out factors of x and y, and I should not think about it as pulling out factors of n. Also, hello to Sophal in chat. Good to see people. We've hit chapter 4, and suddenly, number theory. Here we go again, learning number theory. Will it stick this time? This is, I think by my count, the 3rd attempt that this live stream has had, by which I mean me, the 3rd attempt that I've had on stream to try and learn which numbers are the sum of 2 squares. And I over 3 attempts, the answer has sunk in. I now know which numbers are the sum of 2 squares, but not the proof. Maybe in 2 or 3 months of looking at this textbook in the future, we might get down to a proof. Who knows? Here we are then, back at quadratic forms, thinking about a common divisor of all of the coefficients, which means, well, you're only going to make multiples of that, aren't you? So first, maybe divide by that, and then if you want to put the factor of 3 back in, go for it. You can now make 3 times whatever I just said. Good stuff. Right. Multiplying all the values of the effect of trivial most devices restrict extended forms, greatest common factor, primitive forms, yes please. Primitive forms correspond. Primitive pairs correspond almost exactly. Here it is. It's the admission. Oh, we've done this so many times already to say that vectors are kind of a bit like the fractions. The only ambiguity being that these things correspond to the same fraction. Does not affect the value of the quadratic form. Okay. Being a function, right, so for this thing there is a function x over y. Can I see which one? Probably a times that thing squared plus b squared or something. We're not excluding those which correspond to the fractions 1, 0 and minus 1, 0. 1 over 0. Yeah, okay. So if someone shows you a fraction, and you say, well, I can't really put that in my quadratic form, I need 2 numbers, and they say, fine, let me just split my fraction into 2 numbers. Now you can put it in your quadratic form. Yeah, and you say, okay, please give me coprime numbers. When you write your fraction, use coprime numbers, and that gives us a value of the quadratic form. Yeah, fair enough. Okay. Please evaluate it for all coprime pairs of numbers. You can stack them as a fraction if you like. This whole textbook has flipped between having kind of vectors and matrices versus fractions and numbers. There's things moving around. 3rd time's the charm. Thank you, Mary. Right, okay. Ooh, there's a new picture. There's a new picture. I could have done with this a couple of weeks ago. We drew a version of this. I think I remember drawing a version of this on. I was trying to work out why everything had degree 3. I mean, they're all triangles, but every point's got degree 3. We have a nice graphical representation of all rational numbers. People on the stream have seen this a few times now. Yeah, there they are. Along with plus minus 1 over 0. Here's a picture with the so-called dual tree superimposed. That's a pretty good picture, isn't it? There's some artistry here to decide where to put the middle. I guess possibly right in the middle of each of these triangles. It's pretty good. I like it a lot. So it's kind of binary tree up here and binary tree down here. The kind of novelty, which maybe everyone's seen, I hadn't seen before, is that if you glue together two binary trees with an extra edge between the tops, then you get a tree where everything's got degree 3. Degree 3 on the way down because you keep splitting in two, but then degree 3 if you join two of them together, so sort of left brain, right brain kind of thing. It's that everything having the same degree thing, which is why we can do these transformations, right? We're imagining pushing a stripy sock through a mangle or something, and as we do that, maybe this is nice. So you can imagine, as you pivot around here, this stuff, everything below here moves over there. So all of this branching stuff moves over here, and everything that was over here moves further down over there. So you sort of, if you plan ahead, you could push things in different directions to sort of use these rotation sort of operations that we've seen in Desmos to push things either that way or that way. And if you plan ahead, then you can put in the right kinks and corners so that it ends up being on your favourite edge. So that's like sort of at the end there, that's to the left of this turn. So I should start by going left. So I start by pushing it right or something like that. There you go. Right. Okay. The topograph. Fun. Ooh, here come some numbers. The dual tree has a vertex in the centre of each triangle, has an edge crossing each edge of the fairy diagram. We can only draw a finite part. The actual dual tree keeps branching off forever. The tree divides the interior of the large circle into regions, each of which is adjacent to one vertex of the original diagram. Each of which is adjacent to one vertex. Each region is adjacent to one vertex of the original diagram. Each region is adjacent to one vertex. Region. I suppose, look, oh yeah, okay, so the region has a kind of... If I kept going, then I would draw in more and more edge in here, but then this region would include that 1/2. What's going on there? So the semicircle has, I suppose it has a kind of midpoint in it. And then all the stuff is going to go on inside each of these two semicircle bits. So there'll be some lots of branching over here, lots of branching over there. But this 2/3 will be a kind of point just on like the corner-ish kind of point of that region. Okay, so for each region you get one of the fractions. They could claim that region, one of the fractions. We can then write the value of Q in the region. Right, yeah, you could, I suppose. So here is that picture again, but writing in the value of Q, so you're taking the fraction, by which I think they mean kind of a pair of numbers, and writing in the value. And now you're going to tell me something mad, like you just add the numbers together, right? Then now it's going to say something. The point of doing that is like, oh, you just multiply all the adjacent ones and do the transformation, and wow, it's all good all the way in. Something like that, isn't it? Look at this. This is pretty good. 3, 4. It's got a weird priority order on these regions. They've got a lot of sides, then adjacent to a lot of things. Like this 2 region is a good one to look at because it's adjacent to the 5, the 13, the 25, and then so on, and more stuff. Okay, so you've got this region, lots of stuff going on. Okay, for example, 13 represents the value of 2 squared plus 3 squared. This one represents 2 squared plus 3 squared. And the 29 in the region adjacent to 5/2, oh, so somewhat totally different. Over here, this 29 means 2 squared plus 5 squared is 29. These are the values you can make by adding together 2 squares. It's something I think I care about. Okay. If you're a prime number and you're the sum of 2 squares, then, in the complex numbers, you factorise, because the sum of 2 squares is the difference of 2 complex squares. So you're not a prime anymore, you've been factorised in complex numbers. So if you're a prime number in the reals and you would like to stay prime, I should say integers, I suppose. If you're a prime number in the naturals and you would like to stay prime in the Gaussian integers, then you need to not be the sum of two squares. Don't be like 29. 29 is the sum of two squares. And 5 plus 2i, 5 minus 2i, they multiply to 29. Factorised it. I'm going to factorise numbers in the Gaussian integers. Anyway, this is called the topograph of Q. It turns out there's a very simple method for computing the topograph from just a very small amount of initial data. It's called the arithmetic progression rule. Here are some regions. Here we go. Here we go. If the values of Q in the four regions surrounding an edge of in the tree, so you're going to start with the values 1, 0, and 0, 1, which is like A and B for your quadratic form. So I've got 2. Hang on, and these minus ones down here are going to be A plus B. Okay, maybe this will turn up in a second. P, Q, R, and S is indicated in the figure on the right. So Q and R sharing an edge. Everything's got degree 3, so it has to be like this. Then the three numbers P, Q plus R, and S form an arithmetic progression. Brilliant. Lovely, lovely. So in the picture, I was going to circle this sort of 2, 2, 2 is an arithmetic progression, but not a very interesting one. And then, so then the observation is 1, 3, 5 is an arithmetic progression. And then reading, let's go for an interesting one across here. 1, 7, 13 is an arithmetic progression. Okay, so you keep going in that way. Yeah, it's like a little Feynman diagram, doesn't it? Two things combining and then maybe spitting off a photon or something. It's also the shape that you draw on the faces of a cube if you want to build a budget model of a dodecahedron. Yeah. If you don't want to cut out an actual dodecahedron, but you can do a cube, then you draw this shape on the faces of the cube to make a kind of budget dodecahedron. If you do this on all of the sides, you have to rotate the shape around every time you cross an edge, so that you get, so that's given it 2 sides, but then you do 3 sides over here, like this. So you get 2, what do? I do 2 more sides here. Then you get pentagons. There's 1 pentagon. You get a pentagon for each edge of the cube, and cubes have got 12 edges, so you get 12 pentagons. Each one's got a fold in the middle, sort of budget dodecahedron. That's the thing that I'm holding in my departmental photo. See if I can find it. Budget dodecahedron. Yeah, so on my departmental page, I'm logged in, so this is going to look a bit weird, but on my departmental page, I'm holding this dodecahedron thing. Just this budget dodecahedron with all the like pentagons. Good. So if you need a dodecahedron in a hurry, but can't be bothered to cut out all the pentagons, then you can just draw this shape on the faces. It's also the shape that you get. Sorry, it's maybe my favourite little doodle. You said Feynman diagram, and that's got me going on this. Got me going on this kind of shape sigil thing. Oh, I've turned to too many pages. No spoilers. It's also the answer to the road network problem. If you have 4 networks, I guess it's not spoilers because I'm just telling you the answer to a problem. If you have 4 cities, A, B, C, D, and you want to build a road network that connects all 4 of them. So for example, you could draw roads like this with a humongous roundabout, I guess a tiny roundabout for maths reasons, but draw a road like this that connects everything to everything. Or you could join all of them to London. That's a little bit worse. It's more road network to do it like that. Or you could do, that one would be London if we were going to do it like that. London. Or you could do 3 roads like this. That connects everything together. But that's a bit worse again. The best thing that you can do is this shape. like in the picture, with 120-degree angles around these points. It's also the shape that you get if, because of the angles, it's also the shape that you get if you have a very thin gap between two plates, and you put in 4 pegs, and then you dip it in soapy water. You dip it in soapy water, and it comes out with a soap film, and the soap film makes that shape because of 120 degrees. It's kind of bubbly fact. Little soap films form between the two plates, and you get 120-degree angles. So you could plan the road network by using the soapy water. Anyway, so this is a sort of thing that's turned up in this maths problem 19 and in dipping soapy water. And also, if you draw on a cube, you get a dodecahedron. So when I see this, I think of like 3 other maths things. And you say Feynman diagrams. So now I'm going to think of 4 things. Brilliant. Right. Sort of want to get rid of all of that. It was quite fun, but totally irrelevant. Oh, not the cube. The cube can stay. Is now the time to talk about my thesis? Probably not. I'm on a tangent, but not that much of a tangent. So thesis has got a lot of coalescence going on, and it's got bubbles in, but irritatingly for me, not that sort of bubble. There's a different sense of bubbles where you have underwater bubbles, are kind of more like a sphere of air surrounded by water. So there's no film there. It's just one thing inside a second thing. Whereas a soap bubble floating in the sky is probably something like air on the inside, air on the outside, and then soapy water or something in between. So kind of 3 layers. Underwater bubbles are just a sphere of air, which means that they don't look the same. They're not as nice, but those were the ones that I worked on. Anyway, long time ago. Right, let's think about this arithmetic progression rule, because this seems good. We can check this. Yeah, we can go check it. I just circled some things. Don't make me circle them again. You've picked the same ones as me. Brilliant, okay, great. Similarly for all the other edges. Should we prove it? Let's prove it. Let's prove it. Oh, that's ambitious. Can I remember why things are connected? So to remember, I'm going to have to remember what these things mean. And these are 2 things that are secretly connected by an edge. And then that region is the next edge. So to understand this fact about the values of the quadratic form, I need to understand what fractions there were hiding around here somewhere. Maybe I should give them all names, like, what do I want? So yeah, lines in this diagram mean we're crossing, because they're joining up triangles. So they mean we're crossing an edge. So it means that there's edges that go from this one to this one to this one to this one. And over here, there's edges that go around here. And then there's each of those dotted edges means AD minus BC is 1. So we know lots of facts. The beehive things are hexagons, right? So floating free in space, a bubble would like to be spherical. If you want to squash lots of them together, then they go hexagonal, I think. Mary's seen some videos. You tile the surface of the cube with. You can tile the surface of a cube with pentagons quite easily. Yeah, sorry, I missed that. I missed that thing in chat. You can tile the surface of a cube with pentagons, 1 for each edge, and everything's okay. Just by drawing that elongated X symbol on the sides of the cube. Let's have a think then. So the numbers are like this. QXY. Right, I think this is going to be a sort of matrix fact ultimately, isn't it? The QXY, because there's a way to turn quadratic forms into a kind of matrix with b over t. So maybe if I give these all names, not sure. Just seen the time. And you've got like q of xy over here, q of ab, q of cd, and then over here magically I need to get to like u over v or something, which has also got. It's also related to those ones. Somehow q of that one is an arithmetic progression. It's twice these minus that. Oh, arithmetic progression just means that the opposite things add up. So twice the middle? Twice the middle ones? So if I look back at this one, a different way to say this is that twice the middle is the same as the outside ones. That's not too bad. Twice the middle. Can I just brute force this? Twice the middle things. Twice the middle and the outside things. I've picked a quadratic form now. Maybe that was an error. If it's true for all quadratic forms, I should just check it for squaring, right? I should just check it for numerator squared and maybe xy. And then denominator squared will be fine because these things are just added together separately. So I should check it for like my favourite quadratic forms, these ones, and then everything will add together separately because this is additive. Q is linear and ABC. This is a thing where we're just adding together values of Q. So check it for my favourite quadratic forms, which is like saying just the numerators. So we have x squared and u squared, and we would like to know about 2 times a squared plus c squared, armed only with facts like AD minus BC is plus or minus 1. Doesn't seem likely that I'll be able to turn that into anything. Doesn't seem likely. Wait, could you draw a cube on a tetrahedron? So there's also ways to draw the other Platonic solids on cubes, of course. If you have your favourite. The way you draw a cube on the way you draw a tetrahedron on a cube is to just put diagonal slashes on all the sides. Can I change colour? I think this has got colours, yes. Colours are a little bit confusing. If you do that, then you get a tetrahedron. Every vertex has got 3. Only half the vertices are really involved. Yellows for triangles. Can you draw a cube on a tetrahedron? I reckon you probably can. I need to draw the opposite of that picture, don't I? So if I start with my tetrahedron, then can I draw the kind of opposite thing on all of the faces, which would be, I want twice as many corners, please. So maybe I draw it in here. I would like these ones to count as well. Let's draw in here and round the back. I think that's going to work. It's going to be a bit twisted and weird. Have I got enough squares? Yes, I do. I've got 6, 1 for each edge. And then I could draw a dodecahedron on top of that. And an icosahedron while you're there. Why not? Do the dual polyhedron where you join up the join the midpoints. Join the middles of all the shapes. Yeah, I never thought about that. I don't know. Can I make a tetrahedron? I probably can make a tetrahedron. It seems fun now. Make a tetrahedron. Draw the kind of join each face. On each face, join the vertices to the midpoint. That's now the edge network of a cube. But then also you can do a dodecahedron. And this is because A4 is a subgroup of all of the groups of symmetry of the Platonic solids. Maybe something like that. So let's see if I can draw my little sigil on here. Which way around do I want to do this? Possibly I want to cut in a triangle like that and a triangle like that. Do I want all of them to point in the same direction? Yes, I rather think I do. Yeah, so if you draw triangles on here like this, in kind of Isle of Man style with the 3 bent legs on, and then make these, so then where are we connecting? So there's just a few more edges to draw. They go maybe to the midpoint maybe to the midpoint of the edge. That's not an actual corner, that's just me joining things to the midpoint of the edge. Then coming over the other side, you end up with, as I'm sure you can see from this incredible diagram, really clear, you get a pentagon. 3 on each face. Because 1, and then a second one, and then a third. A threefold symmetry going around. I've broken reflectional symmetry by doing that, so maybe I don't mean A4. What do I do? A4 is just the rotations. Right? Yeah. Yeah, so you draw something like this on each face. Let's do a printable version for people to use at home. That's totally how this is going to be used. So you have an equilateral triangle for the side of your tetrahedron. And you draw lines to the middle of each side. Those are for the cube. They're not actually part of the dodecahedron, but they're the edges. These give you the edges of a cube. The corners count as well. And then you draw, I'll just do a flat version over here to make it a little bit more clear what's going on. You draw these things that also connect inwards. So like this. So you go into a point inside that triangle and out to the midpoint of the edge, into a point inside the triangle and out to the midpoint of the edge. And if you draw that on each face of the tetrahedron, refresh. If you draw that on each face of the tetrahedron, then you get, when all the dust settles, shapes that have 1 edge, 2 edge, 3 edges, half an edge here comes around to 4, and then 5 when it meets up with this bit. So this bit plus that bit is a pentagon. How many pentagons? Well, 3 here, and then times 4 is 12. There you go. So if you draw that on the faces of a tetrahedron, you should get something that is like a very squashed, underinflated dodecahedron. And then you can hold that in your departmental photo for a website somewhere. Good. Yeah, you can see it, right? You can see that pentagon. Kind of a pentagon. This is the worst thing I've ever drawn, but I want that corner. I want that corner. I want that to be a straight line. And it goes across the edge of a tetrahedron, so that's a bit awkward. But I want that to be a straight line. And why does that look so bad? Oh, have I connected it wrong? Yeah, some of the connections around here are not good. You've printed a tetrahedron, that was quick. Yeah, because that corner is different from this one. And that one's not a corner. This diagram's a bit of a mess. Straight line. Lovely. Good, right, okay. You have to get the orientations for the tetrahedron the same on each face. Good, okay. Am I going to prove the thing? I'm going to do about 3 more minutes of messing around with this. Maybe not even 3. I can't see how at all you would prove this. So the given facts, I'm going to show that this given, and then the given facts will involve all the other numbers, like y, d, and b, the things I've been ignoring. Is there a fact about a triangle that I can use? But given that it's a triangle, yeah, given it's a triangle, some of the numbers are just, there's this median rule, right? Some of the numbers are just the sum of the numerators and denominators of the other one. But which ones? Which ones? Don't know. I don't know. Yeah, okay. Going across this one, it was the case that these numbers 1 over 2 and 2 over 3 are formed by the median operation on these pairs. So like 1 over 2 is formed from the median operation, adding the numerators and denominators, and then 2 over 3 is formed by the median operation going that way. But in a general point, I can't see how you'd know which way around it was. Does it matter? Yes. Without loss of generality, you going in that direction necessarily? Rather than from top to bottom, you go from left to right? Don't know, you can have a quick look at the next page. You start from a vertex where you know all three values, and then you can work your way outwards. You have 1, 0, 0, 1, and 1, 1, which is the 1, 1 up here, maybe. Yes, and the 1, 1 is down there. Oh, x squared minus 2y squared, I like that one. Gives you approximations of root 2. Gives you approximations of root 2 around here, maybe along this line. Positive and negative stuff. These points are going to be close to root 2, aren't they? These points are going to be close to root 2 because these are values of x and y such that x squared minus 2y squared is about 0. This line which highlights the bits that switch from positive to negative, absolutely going to zoom in on root 2. I think the book's getting somewhere. I'm miles behind. Okay, so once you know these, you can fill in the others by saying 1, 5, 9, 2, 12, 22, going up in a sequence, and then so on around here. 3, 25 is a difference of 22, so I should add another 22. It's not a difference of 22 at all. 9, 25. 9, 25 is a difference of 16, so I should add another 16 to get 41. Truth. Good, okay. Just the same, negative values. Yes, edges that separate positive and negative. We'll put a later special shading. The fact that the values in the lower half are the same as those in the upper half. Yep, negative numbers are like that. So not always a quadratic form. Whose topograph has these three numbers surrounded by a surrounding vertex, since it could be that. You have three favourite numbers. Yep. Okay. Oh, right, here's a proof. What's the proof like? Oh. What? So the labels on the P and S regions are the fractions shown. What's going on there? This is a good understanding of the median rule is needed. Like sum and the difference. Huh. Yeah, okay, we'll leave that, I think. We're going to come back with a bit of a huh. This is the understanding that I was fumbling around for, which is how do I turn this AD minus BC into a fact about medians? And apparently you just write down the medians and say that's what they must be. Is it the median has to be around here somewhere? And the median has to be around here somewhere because we were constructing this diagram by drawing in the medians, and each edge is only actually adjacent to two triangles, so I guess here they are in some order. That's so stupid, it's definitely that. It's definitely that. The edge is only connected to two things, and I can think of two things that it should be connected to. Oh my goodness, right, okay. So there they are, and then you're just going to go and plug it in, aren't you? For quadratic form, we then have, here we go, A, B, yeah, fine, C has this, P has this, you plug in that one as well. The omitted terms are the same in both cases. They don't involve in terms of they haven't even written it all out. Okay. Add them together, cancels out, plus and minus signs, giving this thing. P plus S is twice Q plus R, which is your arithmetic progression thing. That's worth reading. I liked that a lot. There we go. Brilliant. Okay, and there's some exercises, but next time, periodicity, separate a line, root 2 is around here somewhere. We'll be back, I think, next week. As always, checking what I'm doing. I think I'm back next week. Yeah, back next week for more chill maths. Thanks for joining in. If it's your first time joining in, good to see you. Even if it wasn't your first time, good to see you in chill maths. These are really useful for me to learn maths and build things that I wouldn't otherwise think of building. So thanks for that motivation. It's been really good. Oh, thanks, Keat. Yeah, I thought that might have happened. Thank Keat5. I did a math masterclass. I used some previous slides that mentioned Twitch. Shouldn't have done that. There you go. Good to see you, RFL. Until next one, so we'll do professional live stream for work. If you're not aware of that one, Oxford Online Maths Club. This week, I think it's going to be me plus return of a previous guest talking about spherical coordinates, spherical triangles, and possibly solid angle, the 3D equivalent of angles. We'll see how much of that we get through on professional live stream. Whereas chill math stream is going to be reading a textbook. Now that I say that out loud, reading the textbook sounds like the professional one, and spheres and triangles sounds like the unprofessional one, but weirdly they've got the other way around. What's the Academy of Useless Ideas? I don't know the Academy of Useless Ideas. And also, can I remember how to raid? Look, okay, right, there exists a Twitch channel. This is how I do raids. There exists a Twitch channel. It's called Academy of Useless Ideas. N Stucky says it's good. Follow N Stucky over there next. That's your challenge. Until then, have a nice weekend. Bye. I'm stopping the live stream now.